Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in the Resolved series in which I bring forward to you concepts or problems in which the explanations are not very satisfying in the textbooks, and usually teachers do skip the explanation part to the solution of the problem. So our main aim is to solve a very standard looking problem that you can find in many coaching materials about equalizing levels of a vessel and the time duration for that calculation, and also look at the idea of whether Bernoulli's equation is applicable between two points, especially the points on the top of the liquid. Okay, so I'll try to produce two methods, one of which would obviously be the wrong method that one of my students asked quite a few years ago, and recently in one of our Telegram groups and also Discord server, that method has been brought up to question why that is not giving the correct answer. So we'll try to see all these things during the video, and also stay till the end of the video. As is the case with any of the resolved series situation, it's not just about solving the problem, it's about resolving the concept. So we'll round it off with 6 practice problems to finish the video. Okay, so here we go with the formal wording of the two problems which I actually presented in the previous resolved series. Okay, so this was the practice problem 3. Okay, so I'll come back and read the question. So this is a very standard problem where you have a vessel on this side and a vessel on this side which is initially empty, and there is a small valve of area small a which is very small in comparison to this capital A, wherein the vessel equalization of the liquid takes place, and the time duration options were given. Okay, so this is the first one, and the second one is the investigation of the Bernoulli's theorem, whether it is applicable from point 1 to point 3, point 1 to 2, or 2 to 3. These were the options. So you might sorry, you might be wondering whether these practice problem 3 and 4, right? So it is actually a part of a bigger video, which was the last resolved series video, in which 7 practice problems were given, of which these were 3 and 4. I wanted to produce them in the quickies, but since I wanted both the problems together, I've converted it into the resolved series video. Okay, so that's it. So let's move ahead. It's not about one problem and the other. We'll solve them simultaneously. Okay, so here we go with the formal wording of the problem. Okay, so in case you are visiting this channel or for this particular problem for the first time, give a pause, try this particular two problems in sequence, and then do come back for the problem solutions and also the practice problems at the end. Okay, right. Two cylindrical tanks having cross-sectional area A and 2A respectively are kept on a horizontal floor. First tank is filled with water to a height h and the other is empty. If two tanks are connected by a pipe of cross-sectional area small a, very small compared to capital A, at the bottom, at t is equal to 0, and the time t when level of water in two tanks becomes same is. So treat water as non-viscous liquid. This is the idea that he has given, and you're supposed to solve for it. And the second one is, I've already told you whether your Bernoulli's equation is valid from 1 to 2. 2 is the point, any point inside this small valve, and 3 is a point on the top surface of the liquid in which the liquid is rising. Okay, so let's move ahead. Let's start with a method one. Okay, right, lot of things on the board. What I did is, whatever solution that one of my students in the Discord server has asked me, I have presented it here as it is. Okay, so I didn't want to write it on my own, so just wanted to give the same solution, and let's try to see what went right or wrong in this particular situation. Okay, so what he said is, let the height h be the height of the fluid at some time t inside this side. Okay, so this is small h, let's suppose. At the equalizing level, that means once finally the liquid equalizes on both sides, the a1h has to be equal to a1h1. h1 is, let's say, final equalization height, which would be same on both sides, right? So what is the a1h? a1h is the total volume of the liquid on this side. We will substitute a1 is a in the end. So this is a1, this is a2. So a1h is equal to finally a1 plus a2 into the equilibrium height, which I'm calling it as h1 in that solution. Okay, right. So you know the final equilibrium height on both sides. Now what that student is asking is, let's assume that Bernoulli's equation is valid from here to here, 1 to 3. And we're going to write the value of the pressure plus rho GH plus half rho V square is equal to pressure here plus again rho GH plus half rho V square. The height difference between the two is the rho GH term itself. So he has directly written that term, and P atmosphere on both sides, he cancelled it off. Okay, so he writes that value of the velocity here is V. Then the value of velocity here, he substitutes it with the continuity equation, which is valid because of the mass conservation. So these are there are quite a few number of steps that he has written here. So I think you can manage writing those things. What is this height h? This height h, he has written it using this factor here. Okay, right, at any arbitrary instant h. Now rearranging, you end up getting this function where h at any instant can be used to calculate the velocity as dh by dt. Okay, right. So the plus or minus depends on whether you are taking h on this side or h on this side. And then when you rearrange and solve for the integration for the dt on the left side and dh on the right hand side, with h varying from capital H, the first height, and the last height, as already I told you here. Okay, so when you rearrange, you get something very nice. Root 2 h by g is the dimensions of time, and there is a factor of areas. First things first, if you substitute a1 is equal to a2, it gives you an idea that if both the areas were originally the same, then there won't be any equalization time required. That looks fine, but substituting only one condition is not the correct way to go ahead. Okay, and what strikes you here very quickly before we analyze the conceptual mistake, the mathematical and physical error here is that there is no small a. Small a is the area of this valve, and commonsensically speaking, you should realize that if this valve was thicker, then the time duration should be shorter. Okay, so we expect the time duration to be dependent on the valve's cross-sectional area, which never featured in this. Why didn't it feature? Because we used Bernoulli's equation between 1 and 3 and continuity equation between 1 and 3. We never required the parameter of small a. Okay, so that is what this method 1 solution does. It gives us independent of a, and there should be something wrong about that. Okay, so let's investigate the conceptual error now. Why this Bernoulli's equation is not valid from 1 to 3. So let's move ahead. Again, a lot of things on the board, just concentrate, I'll take you along. Okay, now the idea is, if I look at the left side vessel where the liquid is going steadily down, why is this assumed to be steadily going down? Because the valve size is so small, you are well within your rights to assume the liquid level falls very, very slowly. That is why we are able to use Bernoulli's equations. Otherwise, actually there is a small acceleration that should forbid us from using the Bernoulli's equation. So here we do it because of small a, very small compared to both these areas. Now these streamlines try to squeeze into this valve, and as you could see, they will become more crowded, and that's what represents the higher speed. Okay, so we expect the speed here to be higher. But you carefully observe on the right hand side, the streamlines won't continue. It's almost like these water molecules or water elements are going to hit a big mass, a big chunk of mass, and have inelastic collisions. These collisions ensure that there is some energy losses, and therefore there won't be any streamlines at this place. You don't expect the streamlines to be going from here in this particular direction to these places like this, similar to this side. This would be streamlined. Even in the valve there will be streamlines, but the streamlines would get stopped here, and this would entirely act like a piston, almost like getting pushed up in a very slow manner. It's like an entire entity going up. Okay, so there won't be any streamlines. So if someone asks you Bernoulli's equation, why is it valid from 1 to 3, you could say that there are energy losses due to inelastic collisions that are happening. So is Bernoulli's equation still valid between 1 and 2? Yes, it is, right? So because the streamlines do exist up till this point, there is no obstacles, there are no collisions happening up till this place. It happens just after. Okay, so just to conclude, the continuity equation is valid. It is valid from 1 to 2 and 2 to 3. Continuity equation is never related to energy conservation. It's related to mass conservation. So the student solution that I have written in method 1 is valid for continuity wise from 1 to 3. But the Bernoulli thing is not correct. Okay, so energy loss is the reason for invalidity between 1 and 3. Okay, so that means we have already solved the second part of the problem, which is this one, right? So if someone asks you, it is valid between 1 and 2, yes, it is valid. But between 2 and 3 and 1 and 3, anything involving the points inside this vessel, the streamlines have already stopped in this vessel, and therefore anything related to 3 you're not supposed to mark. Okay, so that's what, as a part of that problem, we have already solved it. Okay, so let's move on to the right method. Again, a lot of things on the board. Right now this becomes a very straightforward one. Once you've investigated that it's only valid between 1 and 2, 2 is any point inside this valve, problem becomes purely mathematical now. Okay, so I've written to take your approval for the continuity equation at the top. Okay, so let me write these velocities carefully. 1 represents this v1, 2 represents this v2, that's why small a into v2. 3 represents this layer going up with v3, and a2 is the area of this thing. Small h is the height arbitrary of this side of the vessel, and h prime is the height of this side. Okay, right? And h minus h prime I'm going to take as a variable called y. The difference of the heights, I'll use it as the variable that I'll use for the integration at the end. It's convenient because the final height difference is 0. Okay, so that's what I've written. And the dy by dt is the rate of approach of these two levels in the vertical direction. So this level goes down, this level comes up, so that y is reducing at this rate, v1 plus v3. And what is the value of this v1? If I take common, it will be v3 by v1 here, which I can write as a1 by a2 from continuity equation. So this was written using this. And therefore, rearranging a very important relation, the velocity with which this layer comes down in terms of the dy by dt is writable like this, which I'll use at the end. So keep it aside. Then we move on to the Bernoulli's equation between. Now we are very careful. We are supposed to do it only between 1 and 2. Okay, so 3 terms of Bernoulli at 1 is equal to 3 terms of Bernoulli at 2 with a height difference of h. So that's what I've written, P1 rho GH and half rho V1 square here, and P2, and I'm taking this as 0 level, so there is no rho GH term, and half rho V2 square. I have to go further. For that, I need to make an assumption here, which is a very good assumption that you will all be able to confidently like. Okay, so entire liquid, as I said in the previous slide, that collisions happen here, and this entire part moves like a chunk or a piston in the upward direction in a very slow manner. So this, I can consider it as almost a static liquid with P1 and P3 already at P atmosphere. And not only that, at the level of the valve here, at the level of the valve, which is all the pressure inside this tube, which is a uniform flow, right? All the same velocities throughout. Therefore, this should be of the same pressure as this line. And that I will write it as P atmosphere from this side plus rho GH prime. So this P2 value I'll substitute here. Okay, and P1 is already P atmosphere. So after cancelling the P atmosphere on both sides, you'll end up having a rho GH prime at this side, which I'll take on this side, and left hand side becomes rho GH minus H prime. And this yellow color half rho V1 square, I'll make it go on to this other side, and then you'll end up having this kind of a term. Okay, right? So the value of this half rho V1 square into, and again, this V2 is a very large value. So I'll take the value of V1 out and use the continuity equation from here. Okay, right? So once I'm done with this, I'll end up having a expression which is h minus h prime. Already said it is related to the value of y. Therefore, this is a rho gy. So rho gets cancelled on both sides. This is a root 2 gy. There's a minus sign a2 because this is a minus dy by dt for v1, and as on the square root, and you end up getting all these terms. And when you do the integration, you can take care of the calculation. So because of the length of the video, already I did 2 methods. So when you bring dy and y on one side with a minus sign, you check the calculations here, you finally end up getting an expression of this kind for the value of time. So the time to equalize to rest is coming out to be a1 a2 by a1 plus a2 into 1 by a into square root of 2h by g. That would be your final result. Okay, and with the liquid damped to rest, there won't be any oscillations like this. We have already assumed that the collisions are inelastic in nature, and the liquid is going to damp out. You see any real life videos of two vessels connected with a very thin valve, you will not see the liquid actually oscillate up and down. Oscillations happen under certain other conditions, which I'll take the practice problems for now at the end of the video. Okay, so if someone says what kind of motion is the liquid undergoing, it's the damped situation where the liquid finally comes to rest and without any oscillations. Okay, under that assumption, this is what is going to be your expression. So let me go back and mark the correct answer. A1 A2 by A1 plus A2 for 2A and A will be 2A by 3, I guess. Okay, and this is what I think you end up having. So just check the answer. I was not interested in the numerical part of that or the integration at the end. It's about the concept of Bernoulli's equation and its applicability. Okay, so are you ready for the practice problems now? Okay, so let's move forward. This is the practice problem 1. So when will the oscillations happen and when you can or cannot apply Bernoulli's equation is the theme of the practice problem that we are going to take up today. So this is going to be answered in AITS select series at the end. Okay, so read the problem on your own, comment the answer below along with the timestamp, and I'll respond whether your answer among the 4 options is correct or not. I think you can read through the question on your own. So the idea is here you have a tube, you have a circular cross section, but the entire cross section is the same uniform one. The connecting tube doesn't have a sudden abrupt change to the area. Usually the collisions that happen in the previous problem that we saw happens when the big area transitions abruptly to a small area. Here that such a thing won't happen. Okay, so you need to understand how to solve this one at the pressure at this place immediately after release. Not only that, part B of the question that I would request is Bernoulli's theorem valid at top or any of the points inside the liquid? Let's say I choose this top point and this top point immediately after release. Since there are no collisions here, as I said, the liquid will oscillate, right? No viscosity, no collisions. Energy is conserved, right? So just because energy is conserved, can you say Bernoulli's theorem is valid between top points? If so, why is it valid? If not, more importantly, why is it valid? I would request you to comment in the comment section below. I'll respond. And then practice problem 2 of a similar kind, neglect the edge effects at these places, H1 and H2. This time valve is having the same area as this one. Again, no collisions and nice 4 options, more than one may be correct answer. And again, part B part also, please do comment below with the timestamp. Okay, so let's move on to the practice problem 3. I would like to revive the Olympiad workout series. This is a subjective style problem from a standard textbook, but it's actually a target JEE advanced question. Okay, so just because it's in the subjective format, I'm giving an Olympiad workout series with the diagram here, doesn't mean JEE will not be interested in it. Okay, it's very much within the realms of the JEE syllabus. And first 3 problems, A, B, and C, are anyway prove that kind of thing. So answers are in front of you. It's the option D or the part D that I would be requesting you to comment the answer below. So here he is very smart. Whenever there is an abrupt change in area, there will be collisions, I said, and there would be no oscillations and damping effects will take place. If you want to reduce the damping and ensure that the 2 vessels of different areas do have oscillations, then your connecting valve can change its area, but in a continuous manner. That's the theme of this question, which is a very interesting one if you try it out. Okay, so go through it. I'll answer it in Olympiad workout series. With so many videos coming up and less time that I have, you might have seen that whenever I give practice problems, most often it takes a lot of time when I actually answer them back. Okay, so in case you don't want to wait, either you comment in the section below and I reply. But if you want the detailed discussion, I think you should come and join our Discord server where people pick up the problems from here and everywhere and do have healthy discussions where I will also join in. And it takes much lesser time than producing a YouTube video to have proper discussions there. Okay, so why wait when I can be late? Okay, so please make sure that you do join our Discord server. So it's a serious JE aspirants community which has already built over 600 to 700 people in the last 1 week that I have announced this video. And if you are complete beginner about what the Discord server is and complete hater of Discord, I definitely am confident that you watching this video tutorial for which the link I shared below or in the I button above, you will definitely be able to understand the importance of it. And do join and check it for 2 or 3 days. You will see how well the things are going there and how quickly the problems are getting solved amongst students along with my help. Okay, so let's move forward to the fourth practice problem. This is also from AITS Select series. Again, an investigation into how the streamline map will be there when there is a discontinuity of not areas but densities of liquids themselves. Okay, so we have hole A and hole B, and I'll take up a separate video for this. I have many things to say about the streamlines when densities of two immiscible liquids are taken into account, and 4 options for the speeds and forces calculation, right? So please go through this, read the question, match the answer, comment the answer below with the timestamp. Timestamp is important. It's comfortable for me to respond. Okay. And the fifth one is a slightly more practical problem. So try to see this. It's a chamber lock question of a ship. Some of you might have never seen the situation or understand what this situation is. Try to Google for the chamber lock, a ship passing through a high tide and a low tide part of the situation. So you'll understand how it is. Try to read it. It's a very, very important concept that JE can touch upon in the future. Okay, so try to comment your answer below with the timestamp. Okay, and last one, pathfinder question. Again, the same thing. When the levels are unequal but the area of cross section is the same, how do you approach these problems? This one is actually a similar one to the practice problem one that I have given, where circular cross section was there. Okay, so that's it. These are the 6 problems. And if you want to check out the rest of the resolved series, which is one of the, I would say, heartbeat series of this particular channel, where toppers doubts are answered, where textbooks actually skip them. Okay, so please do check out the rest of the resolved series. All the playlists are in the description below. If you're new student, there are parallel series also running. All of them are there in description is waiting below. Just have fun. Okay, so in case you like this presentation, and please do give it a like. Liked videos get spread by YouTube for more people, thereby bringing a lot of serious students to this beautiful channel. Okay, so do share the content, and please, in case you have not yet subscribed, try to watch 4 or 5 videos, and then the decision is yours. Okay, so thanks for trusting me with your time, and see you in the next video.